Thank you, Sergio, for that wonderful introduction. Let me restart the clock here. Can you guys hear me? Well, okay, good deal. Yeah, so I'm hoping to talk to you guys a little bit about quantum computing, a little bit about Qiskit, and a little bit about Galaxy, which is three different, pieces of software that I'm involved with. So I'm a postdoctoral researcher in the Blankenberg lab at the Center for Computational Life Sciences at the Cleveland Clinic. And part of the reason why I'm going to be talking about this today is because we are in a partnership with IBM known as a Discovery Accelerator, where we're trying to leverage quantum computing and AI to accelerate biomedical research. So let me get a show of hands real quick. How many of you have heard of quantum computing? All right, good deal, most of the room. How many of you have submitted a job to a quantum computer? Okay, all right. How many of you are excited at the prospect of quantum computing and AI and accelerating research? All right, that's most of the room, so we're off to a good start. So yeah, I'm just here's a little layout of the talk. I'm gonna give you a brief introduction to QC with Qiskit, a brief introduction into Galaxy as well, and then sort of show you a real world application that we've been working on, which is protein structure prediction using quantum algorithms. And if there's a little bit of room towards the end, I'm happy to take some questions. If not, talk to you guys after the session. So first of all, I'd like to thank IBM for letting me use some of their slides that kind of really break down what the space is and what quantum computing is all about. But why is this technology being developed? Why are we exploring this? Well, the fact of the matter is that there's sort of a bunch of problems that we can't adequately address today. And within that, there's a subset of problems that we can adequately address today classically. And then that's also part of a subset of problems that we hope to address with quantum and classical computing at some point. The fact of the matter is, no matter how advanced AI has gotten, how advanced GPUs and CPUs and parallelizing processes has gotten, we still barely scratch the surface for a lot of problems that are out there. So, of course, in classical computing you have bits and logical circuits. In quantum computing, it's a little bit different. We have quantum bits or qubits. And off the get-go, I just want to show one of the possible things that could make this technology advantageous is we're not just limiting information how we represent it to 0 and 1, but this is actually a sphere, right? And just like how you have cities on a map, somewhere there's a lot of points on a sphere. So we're able to represent information beyond just 0 and 1, but many different points in between. So quantum bits, or these qubits, they are a controllable quantum object, and this serves as a unit of information, much like bits do on classical hardware. And quantum circuits, on the other hand, are a set of quantum gate operations, much like logical gate operations, on qubits, and this serves as a unit of computation. So qubits, information, quantum gates, computation. So what makes this technology unique is that it's actually using essential ideas and harnessing some of the laws and principles of quantum mechanics, the first one being superposition. So superposition is when you create a quantum state that's a combination of both 0 and 1 over here, each with their respective probabilities, A and B. These conditions allow us to map the qubit onto a Bloch sphere, right? This sphere that we see over here. Now, of course, if A and B are non-zero, then the qubit state technically contains both 0 and 1, right? Because when you sum up the square of their absolute values, that sums up to 1. So this is what people say when a qubit can be in a state of both 0 and 1 at the same time, in two places at the same time, or however you want to describe that. Now, when things start to get really interesting is when we look at entanglement. So when you get two qubits, we get combinations like 0, 0, 0, 1, and 1, 1 over here. And what basically this means is when you get this over here, you have the first qubit being 0 and the second qubit being 1. And in this case here, when you take the absolute value squared of each one of their coefficients, that equals to 1, right? Now, if two or more of these coefficients, A, B, C, and D, are non-zero, and you cannot actually separate the qubits, they're entangled with perfect correlation, and they're no longer independent of each other. The other thing that we're using over here is this concept of interference, right? So raise your hand if you've used noise-canceling headphones before. Okay, all right, most of the room. It's sort of a similar thing that's happening over here, right? When you use noise-canceling headphones, you're essentially injecting sound waves that sort of mask, like all the sound that's being muffled from the outside, ensuring that what you're actually hearing is the music or whatever you're playing through them. That's what we're doing over here. We use interference to basically decrease the probabilities of seeing a certain solution and increasing the probabilities of seeing the real solution, right, so to speak. Now, if you want to take a look at what a quantum or QPU looks like, this is IBM's Osprey. It's 433 qubits, where you have the qubit itself, the readout, the wiring, and then this is how they're actually physically connected. So, quick question. Does anybody know where the coldest place on Earth is? Cleveland. Yes, there you go. Cleveland, Ohio. And that's because Quantum System 1, which is, first of all, the very first quantum computer dedicated entirely to healthcare and life science research, operates at 15 millikelvin. So just slightly warmer, ever so slightly warmer than outer space, right? So Quantum System 1 is about 10 feet by 10 feet by 10 feet, and inside of this chandelier that you have over here, you have a bunch of wiring that gives you all the microwave pulses, and over here is the tiny QPU chip. And one of the reasons why we have to keep it at such a cold temperature is, at the end of the day, we're trying to observe these quantum effects and harness, things like superposition and entanglement. And in order to do that, one of the things you have to do is you basically have to create a system that has almost 100% thermal isolation for that. So it's definitely not, it's a little expensive to keep things at almost absolute zero, but that's how we make it work. That's how you can actually see superposition. Okay, but what does this all mean, right? Okay, so every day you got to do a bunch of stuff, right? You might have to work. What about travel? Perhaps you might want to walk your dog. At some point you have to eat, right? Okay, but if you're going to eat, maybe you want to exercise a little bit. But the fact of the matter is there just aren't enough hours in the day to do all this stuff. But what if you could do all these things at once? That'd be kind of cool. Well, when you think about it, that's sort of what quantum superposition is, right? And what if all these different copies of yourself that are doing all these different things, they could somehow talk to each other? You could coordinate what they're doing. In a way, that's what quantum entanglement is. Now imagine if you could have a device that computes that can harness these properties. The result, in a way, is the ability to sample large search spaces simultaneously. And ideally, this can potentially help us solve some very hard optimization problems. So there's different types of quantum computers and different types of qubits. On the one hand, we have the superconducting qubits that you see over here. This is what Google, IBM, Rigetti, and D-Wave use. We have the trapped ion qubits that you see over here. That's what Honeywell IonQ uses. We have silicon quantum dots, which have been around for a while. That's what Intel and HRL uses. And finally, we have these topological qubits, which is what microwave uses. Now, the most commonly used qubit today is the superconducting transbond qubit. This is, again, what IBM uses. We've all heard of semiconductors, right? I mean, that's what pretty much all computers use, but these are superconducting. This is because there's virtually no resistance in the circuit when you use this material. They're all described by the three same non-dissipative elements, right? So you have a capacitor, which is a linear circuit element. You have an inductor, which is another linear circuit element. And then you have this Josephson junction, which is a nonlinear circuit element, which is what you see over here between the qubits. Now, what makes these desirable for this technology is that they have a very strong coupling to electromagnetic fields, right? What's happening when you're running these machines and you're running these circuits is you're shooting microwave pulses to them, right? And because it can couple very well to electromagnetic fields, you can actually use microwaves rather than other higher energy, radiation. You don't have to go into like X-rays or anything like that. So that's very favorable. You don't have to use lasers. You can just use microwaves. Of course, the downside is you have to work at nearly absolute zero. Of course, every one of these might be a little bit different, but for the most part, they're made up of two pieces of aluminum film that are evaporated on a sapphire substrate. Of course, all these companies that make these things might have subtle variations of that material's chemistry, but that's sort of the scaffold, I guess you could say. Okay, so when we talk about quantum computing services, this is kind of what it looks like. We have the end user over here with their laptop, and then some sort of a software stack in the middle that allows you to code and create the circuits. In this case, it's Qiskit. And then you have some sort of cloud service, which is Qiskit runtime in this case. And then you have some sort of server in the laboratory. And then you have the control electronics, which are like sort of like the last stop between all of this and the QPU. And this is what kind of actually converts your circuit into the series of microwave pulses on the QPU. But this is a Python community from what I gather, right? So I'll just say this is just Python with a twist, ladies and gentlemen. So if you're comfortable with Python, then you're like 75% of the way easy, all the way there. The remaining 25% or so is being comfortable with quantum information science and quantum mechanics and that sort of thing. I'm a computational chemist or computational scientist, which means that I'm a chemist that just barely knows how to type and knows enough computer science to simulate molecules. So it's actually been kind of a hurdle how much Python you have to know to do some of this stuff. But fortunately, the folks in my group are really good at computer science and have kind of like held my hand along the way. But again, you just import modules, you import a certain class, you pass certain attributes to it. Like for example, over here, we're importing quantum circuit. We're setting QC as quantum circuit with 2 qubits. we're giving one gate, the Hadamard gate, which creates a superposition to qubit 0 over here, and then we're adding a CNOT gate between qubits 0 and 1, which actually, entangles the qubits and flips one qubit if the state of the first qubit is 1. So this is an example of final result, right? Even though you're sampling states that are in between 0 and 1 and all these different combinations, ultimately when you measure, when you take your measurements, things collapse to 0 or 1, right? The way you can think about it, so you can think about superposition if you play a guitar chord, right? You can hear, one sound that's made up of all these different melodies. Now, in a quantum system, when you do that and you actually measure it or hear it, you hear the individual notes, right? So when we actually measure it, we go back to binary at this point with respective probabilities. And here we can see that the highest probability is this, given on the number of counts that we see here, is a state 0, 0, 0. Okay, so Qiskit patterns is the fundamental steps in a quantum computing workflow. So the very first thing you're going to want to do is you want to map your problem to quantum circuits and operators. And after that, you want to optimize your circuit for target hardware or transpile it, right? So we use this term transpiling, which is essentially, what compiling is, right? And most of the days, when you're using Python and these higher abstract languages, you don't have to think about, compiling anymore, right? You just import your libraries, you just run your programs, and you don't think about what's happening down at the hardware level. So this is actually one of the things that makes quantum computing a little tough to get into, is that you have to actually compile things from scratch, and that we haven't done that for a while. And then after that, you execute things on target hardware, and then you post-process your results to get some sort of relevant data that's relevant to your particular line of work. In our case, it's biophysics and chemistry and that sort of thing. So to map a problem, first you start with some sort of numerical representation, and then you map this numerical representation into some sort of quantum computing representation. So you map your problem into qubits. And then you choose a quantum algorithm that's going to help you solve how you formulated this problem, right? And a lot of times it's a variational algorithm. And what we're doing over here is you're essentially mapping the orbitals on this molecule over here to individual qubits. This is not a trivial process. But I think that for those of us that are in research, it's probably the one skill set that we really want to try to harness. For those of you who are more like, real computer scientists and software engineers, you can definitely get into the areas of error mitigation, because these computers are inherently noisy, right? So other parts of the software stack involve developing methods to mitigate that error, as well as how to best transpile your circuit onto any particular QPU. So whenever you actually write a script to do this sort of thing, there's a few basic ingredients, right? So you initialize the Qiskit runtime service over here, and then you want to set a particular backend, right? In this case, a backend can be a simulator. So whenever you're developing an algorithm, you want to simulate it first, right? You don't want to, spend too much time trying to run it on hardware until you know the way that you formulated the problem itself actually works, right? And if you want to run it on hardware, you could either specify the backend specifically, or you can use this line here, least busy, which is basically saying, give me the least busy QPU right now that is not a simulator. And then from there, you use a particular primitive, right, which is going to encapsulate the results of the quantum computer. It can be sampler, it can be estimator. In this case, it's sampler, which is going to sample those bit strings and give you a total number of counts and a probability distribution at the end. So and then you invoke it and you run it for either one single iteration, right, given a number of shots. And the number of shots is how many times when you submit it, you're going to execute the circuit, right? Because there's a lot of stochasticity and this is probabilistic, so you want to average your results over running the circuit many, many times. So given the fact of how this works, quantum computing could have benefits in optimization, right? So there's a whole field in which you can transform a given optimization problem and use variational algorithms that could provide solutions. And these variational algorithms use sort of a hybrid method, right? In this case over here, you're trying to compute the minimum expectation value, which is essentially the tensor product of an operator and these two wave functions that you see over here as a function of theta. And this theta are the rotation angles around the qubit, right? So you shoot a microwave pulse to these qubits. Those are essentially what the gates are. And those microwave pulses yield a certain rotation around the qubit. And you can actually relate that back to the wave amplitude of the microwave pulse that you're shooting into the QPU. And the way it works is, because one of the things that, we're still trying to explore what exactly quantum computers are really good at, but one of the things that they're really good at is solving Schrodinger's equation, or a wave function. and which has classically been not that easy on a classical computer. It's, some people argue it's kind of a trivial thing, right? So the idea is, well, can you formulate your problem in a way that it sort of, can look like, a quantum mechanical problem, so to speak, right? So that's what's happening over here, right? So essentially you are trying to minimize this cost function, I guess you could say, as a function of theta, and then you loop it out, and then you use a classical optimizer on classical hardware to further minimize those theta values. You get a new set of theta values, and then you optimize and run the circuit again on the QPU, and this loops over and over and over again. And then finally, you end up with a low energy solution, which you could then translate to whatever your problem, your research problem is, whether it's calculating, computing electronic structures of molecules or predicting the structures of proteins, which is one of the projects that we're involved with. Okay, so one of the things that we're trying to do is we're trying to use quantum optimization and apply it to biological systems, in this case, protein structure prediction. So we've probably all heard of that, AI has done a pretty tremendous job at tackling the problem of protein folding, right? And a lot of the deep learning programs have been extremely beneficial, really in a lot of ways revolutionized the field, but they haven't entirely solved the problem just yet. So there's still room for improvement here and there. It's only the hardest problem in biology, right? So it's going to take a bunch of different efforts to make progress over time. But nonetheless, why is it hard, right? Whether you're in biotech or not, you've probably heard that predicting the structures of proteins is really hard. Well, let's break it down for a second, right? So this is what the basic backbone of a protein structure looks like over here. This is backbone, and these are the little side chains that sort of spread out. Now, you can describe the structure of a protein based on these dihedral angles that you have over here. Now, one of these dihedral angles, the omega, that's almost fixed at 180 degrees, but you have a little bit more room in phi and psi, right? You have two predominant states of phi and one single predominant state of psi. So essentially, the total number of shapes as a function of n amino acids, because remember, the amino acids are the little blocks that make up a protein structure. The total number of shapes or conformations it could take is described by this relationship here, 3 raised to 2n minus 1 power. Now let's just say that regardless of whatever hardware that you're using, you spend 1 picosecond or 1 trillionth of a second sampling each one of those possible structures. Well, this is what the time in years is going to look like by the time you sample all the structures as a function of the size of the protein. Now, if we look at over here for 5 amino acids, that's just instant, right? If we go up to 10, double down, again, that's really quick. That's on the order of 10 to the raised to the negative 10 power. If we double down again to 20 amino acids, that's on the order of 10 to the negative 1 power. Okay, so now we're at like 4.5 years at this point, essentially. And then if we double down again to 50 amino acids, now we're on the order of the 10 to the 28th power. And now over here, if we go up to 100 amino acids, which is still relatively small, we're on the order of 10 to the 75th power, right? And I say it's relatively small because the largest human protein that's out there is Titin, and that's 37,000 amino acids in size. So basically, by the time you get to 100, you would eventually surpass the age of the universe in time by the time you exhaustively search the entire space. So when you think about it analogously, it just blows up in a massive search space. Think of a Rubik's Cube that is going to keep increasing in dimensions, right? The number of configurations it could take and the time to solution dramatically blows up. So to simulate the physics of why these proteins adopt the structures that they do is a very hard problem. And that's why the deep learning methods in AI was used to tackle this, because instead of going that route, let's just train on the experimental structures that are out there and try to predict as best as we can. Now, the problem with that is that the experimental structures that the deep learning programs train on, they're about 200,000 proteins. We've been able to derive over 250 million sequences that ultimately correspond to their corresponding proteins. So there's a gap of 200,000, 250 million. So that's a gap of almost 1,201. So for those of us in this community, we believe that there's a lot of biodiversity that we haven't seen yet. So in an order way to overcome the limitations of limited training data, you have to simulate the physics of this, and you have to find an efficient way of doing this. Okay, so let's just talk about the big picture here. The big picture is that on the order of n qubits, they can represent on the order of 2 raised to the n bits, right? For example, if n equals 10, classically you're going to need 1,024 unique bit strings, right? Now, 10 qubits, on the other hand, can theoretically store all these combinations as a superposition of quantum states. So it's a little bit more nuanced in reality, but that's sort of like the big picture. And you can kind of see the advantage that you could possibly have there. Of course, the catch is that near-term quantum computers are noisy, right? And that's where the error comes from. That's why there's entire fields that are just dedicated to mitigating the error in computers. And you also need to have long enough coherence times to get the best results, right? So I mean, like, there's a lot of decoherence when you're running these circuits, and you need to have like long enough times to actually get the results that you're looking for. And it's expensive, right? So maintaining these machines at 0 degrees is not cheap, like I was saying earlier. But do not fret, my friends. The age of fault tolerance is on the horizon, sooner or later. Most people forget about this, but back in the 80s and 70s, and when classical computers really started taking off, like, there was still this notion of fault tolerance. They were themselves noisy, right? And that's the case now. But things like Moore's law still applies to quantum computing too. So it's just every 2 years they're going to get bigger, better, and we're going to have better ways to tackle error mitigation. And one thing, since I did mention the fact that it's not cheap to keep them at 0 degrees Kelvin, I'll just mention this right here. So when you experimentally determine a protein structure, you can use methods like nuclear magnetic resonance. And nuclear magnetic resonance machines, they use helium to cool all the way down to 0 themselves. We're pretty close to it, about 4 degrees Kelvin. And at the clinic, we're actually using the same helium pumps fed into the NMR machines to predict the protein structures experimentally, and that same helium is going into quantum system 1 that is allowing us to predict protein structures in silico. So that's a little fun fact I like to add there. But if you're curious and want to learn more about quantum computing, check this out. IBM has been really, really cool about putting all the training materials out there. You can set up a free plan, which will give you up to 10 minutes to run on QPUs on 127 qubit machines every month. Give it a shot. They have a bunch of really good educational materials, and they're trying to grow the community, so shout out to them. Now, with that in mind, I'm going to switch gears here for a second, because this is also about Galaxy. So we're researchers, and we're also software developers for the Galaxy project. So it's a free open source system for analyzing data, authoring workflows, training and education, publishing tools, managing infrastructure, and much more. And our motto really is, we code so other people don't have to, right? So whether you're an experimental biologist or a computational biologist, there's a lot of algorithms that you have to run, on the command line to get your data, and sometimes that sort of delays research. So we try to take care of that and convert those open source tools. Either we develop our own, or we take other open source tools and turn them into a nice user-friendly interface. Originally, this was intended as a tool for bioinformatics, but due to how well it manages workflows and stores its data, it's managed to evolve beyond to cheminformatics, machine learning, climate science, astronomy, and beyond. And this is a picture of our latest community conference in the Czech Republic last month. Okay, so, and again, I'm not a computer scientist, but if you're curious, I mean, this is a lot of what we're using to make the code work. So on the front end, we're using JavaScript, CSS. On the back end, we're using Python. As far as managing packages and dependency resolution, we mostly use Conda, although we use other possible solutions too. For tool wrapping, we mostly use Cheetah and write XML files for that. For interactive tools, we use Docker. For database management, we use SQLite, and PostgreSQL for the larger public servers. For process management, we use Gravity, which is developed by people on our team. For distributing the compute, we use Slurm, Torque, OpenGrid, AWS Batch, and some other options there. And for the user interface access, we use Unicorn, Apache, as well as some other options. And if you're interested, check us out. It's completely open source. And we have over 10,000 monthly users on our national servers. The repo's been cloned over 250,000 times. It's a pretty wide community. And again, we cover a bunch of different areas of science. And then just shout out to Nate Carrar, which is our system administrator, a brilliant computer scientist who kind of makes the magic work behind the main servers. And this is how we distribute all of our jobs, starting from Penn State, San Diego, the Texas Advanced Supercomputing Center over here, and then there's a couple of Johns Hopkins University, and then we kind of pass things through using Slurm, Kubernetes, and a bunch of other fancy methods. But we distribute the compute all over the place, and most of these institutions have been nice enough to lend us their compute. Okay, so all right, got 5 minutes. This is what the Galaxy user interface looks like. We have a tool panel. You can select a bunch of tools over here. We have the center panel over here. And then we have our history, right? So every time you execute an analysis, you start populating your history, which lets you keep track of your research, which is really neat because research can get very disorganized a lot of the time. And then over here in the middle, in the center panel, you can either use this to visualize. So if you bring up a visualization of your data set, or every time you bring up a tool, all the tool's possible parameters pop up as well. And then you select those. So these are all usually command line parameters that we make visible as, buttons that you can just like play around with and click and drag. Now, when you actually wrap a tool, again, this is written in Cheetah in XML files. So basically, over here, one of the first things you do is you set the requirements right, which a lot of the times they come in the form of conda packages. And then you have an optional block where you can set up a config file. In this case, you're passing your credentials for API for IBM, like your API token and whatnot. And then when we go over here, again, we're taking command line based tools and turning them into buttons and a user interface, right? So at some point you have a command block here, which you would normally run natively in the tool itself. And then we're symlinking all the different inputs that you can have over here, which could either be directly a file that you import into your history, or it could just be something you select. It could be an integer, some sort of Boolean variable. But actually, what really makes Galaxy unique is the ability to create automated workflows, right? So whenever you do any sort of analysis and research, whether it's bioinformatics, you're dealing with large data sets, and sometimes you need to run an analysis hundreds of times, right? So you can create these workflows that you can then execute on a single input data set, or hundreds of data sets for that matter. And you can either, if you're just running an analysis ad hoc in your history, you can either extract everything you did, because Galaxy keeps record of everything that you're doing, or in the workflow editor, you can actually create the workflow from scratch. And this is actually, this showcases that real quick. I'll just show you here. So this is a workflow where we are using a quantum algorithm to predict a protein structure. It sends it to IBM, it brings it back, and we take those raw results, and then we use classical software, such as GROMACS, which is a molecular dynamics engine, to add the missing atoms. It gives it what we call a molecular force field, and eventually it gives us a realistic representation of a protein structure, starting from the initial optimal guess from the quantum computer. And at this point, we have a final refined structure. So this is essentially, these steps over here towards the end are what some of the deep learning programs like AlphaFold does, right? At the end of the day, after you get this raw prediction, you strap a force field to it, and then you finally refine the structure itself to get the closest thing to the most likely biologically relevant shape of this protein. And then finally, you can visualize the structure over here, whichever way you want. This is the ribbon representation, but if you want to see what all the side chains look like and where all the individual atoms are like, you can also do that too, right there in Galaxy. So it really helps with automation, right? So we're sending some sort of job to a quantum computer, and then locally we get it back and we take care of everything else, and all we did was give it that single primary amino acid sequence, and everything else was done automatically. Okay, so if you're interested, give it a shot. Galaxy's awesome. It's a really cool community. These are some of the main servers that are out there. But again, if you would just set up your own instance and give it a shot, you can just clone our repo and set something up locally. I'll be around this afternoon in one of the open spaces if you guys want to talk to me and check this out. I think one of the slots is around 2:15. I can show you how Galaxy works. I can show you how the Qiskit tool works as well. And also, we have a bunch of training materials. So if you do any sort of research in this area and beyond, whether it's climate, astronomy, astrophysics, computational chemistry, check us out. We can walk you through any sort of analysis in this scope that you might want to conduct. Again, come join us. We're pretty cool, just like this Python community. Everyone seems pretty chill. Check us out. You can come join our yearly conference, present your research, collaborate, lead a training session, hack away, meet cool people, and have a fun time. And then lastly, I'll leave you with this.